Alright, so in today's video we're going to be learning about some of the basics of energy. And I'm hoping a lot of this should be review from things you may have learned in physical science in middle school. Okay. So anyway, by the end of this video you should be able to identify when an object has what's called kinetic energy. You should be able to solve problems using the equation. You should be able to identify when an object has what we're going to call chemical potential energy, electric potential energy, elastic potential energy, and gravitational potential energy. And then finally, you should be able to solve problems using this gravitational potential energy equation. Okay? So there's a quick rundown of what we're going to be doing here. It seems like a lot, but it'll go quick. All right, so kinetic energy is energy of a moving object. All right? The more motion an object has, the more velocity that an object has, the more kinetic energy that it has. All right? Because of this, if an object is not moving, then it has no kinetic energy. All right. So it turns out that an object's kinetic energy depends on two things. It depends on the velocity. All right. Technically, it's speed, really. The faster it's going, the more kinetic energy it's got. And it depends on the mass. More massive objects will have more kinetic energy than smaller objects, assuming they're moving at the same speed. Okay. And so here's the equation that we use to calculate kinetic energy. Okay. Now, one kind of nice thing about energy is that it is a scalar, so we don't need to worry about direction at all. Okay. We're just literally counting how much energy the object has, and there's no direction associated with it. All right. So to calculate the kinetic energy, sorry, itchy nose today. To calculate the kinetic energy, it's just half of the mass multiplied by the velocity squared. Notice just the velocity is getting squared there. All right. So let's do a quick example here if I can get my smartboard to work. All right. So in this first example, it tells us that Carl the cat and Dave the dog are going for a walk together, and they both walk at 4 meters a second. All right. So for Carl, here's the deal. So what we know. So here's our givens. Right. I'm very close to the camera right now. Sorry. All right, so here's our givens. We know that his mass is 3 kilograms. We know that his velocity is 4 meters a second. So to find the kinetic energy, all right, well, it's just 1/2 mv squared. So we get 1/2, 3 kilograms. Velocity is 4 meters a second. Don't forget to square that. So half of 3 is 1.5. 4 squared is 16. 1.5 times 16 gives you 24. And the units you get is kilograms times, up here we're going to get meters squared per second squared. Okay? Now, this has a name. Rather than writing kilogram meters squared per second squared all the time, we're just going to call this 24 joules. Okay? Often abbreviated, usually abbreviated, with a capital letter J. Okay? So, energy will always be measured in joules this chapter. Okay? Now, the second part of this problem, I'm not going to actually go through it because it's basically more of the same, but it does have an important point. All right? So now suppose we were to go back and do the exact same thing for, oops, I need that to be a different color. Suppose we were going to go back and do the exact same thing for Dave the dog. All right? Well, if we wrote out our givens, our mass would be 6 kilograms, and our velocity would be 4 meters a second. All right. So how would that change things? Well, let's see. Ke is 1/2 times our mass times our velocity squared. So it looks to me like the kinetic energy is directly proportional to the mass. Okay. So double the mass gives us double the kinetic energy. 10 times the mass gives us 10 times the kinetic energy. All right. And so here it looks like the mass between Carl and Dave gets doubled, right? So if I've got double the mass at the same velocity, we're going to have double the kinetic energy. So Dave's kinetic energy here is going to be 48 joules. Okay? So Dave has more kinetic energy because he has more mass. Double the mass, double the kinetic energy. All right? So now, Carl now gets jealous, right? Carl's like, what's going on, Dave? You just betrayed me. We were on a walk. Now you've got twice as much kinetic energy as me. So Carl is thinking, all right, well, check it out. I know that kinetic energy is 1/2 mv squared, right? And right now, my kinetic energy is 24 joules when I'm traveling at a velocity of, what was he going at, 4 meters a second, right? So he says, well, maybe if I double my velocity, that'll double my kinetic energy. All right? But unfortunately, it doesn't work because look, the kinetic energy is proportional to the mass, okay? But with velocity, it's proportional to the velocity squared. It's proportional to the velocity squared. So take a look at what the velocity squared is. Over here, his starting velocity squared is 16. His ending velocity squared is 64, right? And so because of that, his velocity squared actually increases by a factor of 4. All right? So long story short, this is what's called a direct square relationship, okay? Any change in the velocity affects the kinetic energy twice, or squared, okay? So if you double your velocity, the kinetic energy gets doubled twice. If you triple your velocity, the kinetic energy gets tripled twice, okay? So hopefully you've learned about this in math, all right? So anyway, moral of the story then is if Carl is going at 8 meters a second, his kinetic energy is now going to be 4 times as big, so you get 96 joules. All right? If you didn't completely follow that, it might not be a bad idea for you to pause the video right now and use the kinetic energy equation and find Carl's kinetic energy at 4 meters a second, find his kinetic energy at 8 meters a second, and convince yourself that doubling the velocity makes the kinetic energy 4 times as big. Multiplying the velocity by 10 will make the kinetic energy 100 times as big. All right, this is a really important thing, particularly when we get to car crashes. That's why traveling at high speeds is so much more dangerous, because you have way more energy than when you're going at lower speeds. Okay? All right. One other thing worth noting is this, that if both Carl and Dave stop, then their velocity is going to be 0, which means that their kinetic energy will be 0, right? Okay? And finally, obviously, we can work backwards, right? If I give you Dave the dog and I tell you, all right, Dave the dog has got a mass of 6 kilograms, and I tell you that his kinetic energy, oops, that's an E. His kinetic energy is 300 joules, then we ought to be able to find the velocity, right? KE equals 1/2 mv squared. So, 2 options. Option 1, plug the numbers in and then solve it. Honestly, I think I'm going to do the algebra first, just because it's fairly often that we'll have to do this kind of problem where we got to find, this E is driving me nuts, where we'll have to find the velocity when we're given the kinetic energy. So to algebraify this and solve for V, we got to multiply by 2, so you get 2ke equals mv squared. Divide both sides by m, and then take the square root. And you get V equals 2ke over m square root, okay? That is not an equation that I'll give you on an equation sheet, but it, like I say, it comes up fairly often, so you'll probably memorize it anyway. So his velocity is going to be 2 times 300 joules divided by 6 kilograms, square root it. This ends up giving you 10 meters a second. All right? So there we go. Kinetic energy, all right, depends on both mass and velocity. The next type of energy we need to talk about is what's called potential energy, all right? So potential energy, which we'll abbreviate as PE, is just energy that an object has stored or saved, all right? Usually the way that we illustrate that something has potential energy, because you can't sort of see potential energy because it's stored, so usually the way that we illustrate that something has potential energy is by showing that that potential energy can be converted into some other form of energy, like light energy or sound energy or heat energy or kinetic energy, okay? All right, so throughout this unit, we're going to talk about 4 different types of potential energy, but we're only going to learn equations for 2, all right? And today, we're only going to learn equations for 1 of them, and the second one we'll get in the next video. All right, so the first type of potential energy that I'd like to talk about is what's called electric potential energy, all right? Electric potential energy is energy that is stored up in a battery or other power source. When we get to electricity, we'll learn a little bit more about where this comes from. But basically, it's caused by electric charges, okay? So simple examples at this point would be like a battery or a staticky sweater. Like if you rub your feet across the carpet, you get a static charge, or on the slides at the playground when you're a kid, the plastic slides makes your hair stand up, right? So all of that electric charge results in what's called electric potential energy, okay? So how do we prove that it has potential energy? Well, with static electricity, you can shock somebody and go zzz and ouch, right? It creates light, there's energy. With a battery, you could put it into a toy or a flashlight or something and convert that energy to something else, all right? So anyway, I want you to know that electric potential energy is a thing. We won't really be dealing with it too much except just conceptually. Okay. Similarly, we can talk about chemical potential energy, which is energy that's stored in the chemical makeup of an object. Like gasoline, right? You put gasoline in a car, you burn it, creates heat, and kinetic energy. The car goes. Food. This morning I had some Cocoa Puffs for breakfast. They were delicious. And those give me the potential energy that I can use to convert to kinetic energy to make myself move and run around. All right. So in all of these cases, we've got energy stored that you can't kind of see. We can release it, convert it into other forms of energy. There we go. So that's potential energy. All right. 2 of the types of potential energy. All right. The third type of potential energy is actually the focus of the next video. So I'm going to talk about it only very briefly here. It's what's called elastic potential energy. It's energy that an elasticy object has because it is being stretched or smushed. Okay. If I take a rubber band and stretch it, I can say this has potential energy, right? Because if I release it, then it now has kinetic energy. And so that, where did the kinetic energy come from? It came from being stretched. Okay. Same thing with a spring, right? You can stretch it. It has elastic potential energy. And then some springs, rather than being stretched, they get what's called compressed. In the notes here, I used the word smooshed, right? But you can squish it, and it wants to unsquish, right? And so you're storing energy. Okay? So here's some examples here. Stretched rubber band or slinky, a spring that you've smooshed. An inflated balloon, right? Gets stretched out. If you, let the air out, it decompresses and pushes the air out, okay, giving the air kinetic energy. I've got, you've all got Nerf guns, right? Those have springs in them. That stores up elastic potential energy. Okay? Oh, incidentally, I didn't say. So elastic potential energy is EPE. Electric potential energy, I didn't even comment on this. I'm going to use the term, or the symbol ZPE for electric potential energy. This is not sort of widely recognized notation. It's just my notation. I didn't use EPE because that's elastic. So for electric, I used ZPE as in zap or as in lightning bolt. Okay, so that's why I used ZPE for electric potential energy, if you were wondering. Okay. All right, so there we go, elastic potential energy. All right, and then the last thing we need to talk about is what's called gravitational potential energy. All right, gravitational potential energy, we'll use GPE to stand for it. This is energy that an object has stored because it is being elevated, or because it is elevated, I guess, or being held up above some lower point. All right, so, a person standing up on a ladder, they're up high, they have gravitational potential energy. A skydiver is up high, a skier at the top of the hill, a rock at the bottom of or at the top of a cliff. All right, so why do these have gravitational potential energy? Well, because in each case, if you release the object, it's going to move. And as it moves down, that gravitational potential energy it has gets converted to kinetic energy. So, for example, if I take this duck here and hold it up, all right now the duck is about 1.5 meters above the ground. And because of that, he has gravitational potential energy. All right, if I let him go, he begins to move, right? So all I did is converted that gravitational potential energy of the duck into the kinetic energy of him moving, okay? It's the same as when I take this spring and stretch it up, when I let it, or stretch it down, when I let go of it, we take the elastic potential energy and convert it to kinetic energy, right? Okay. Similarly, when I take the duck and lift it up, it's kind of like stretching that spring, and then when I let it go, it converts back to kinetic energy. Okay? So, any object that is elevated has gravitational potential energy. All right? If it's at its lowest possible point, then it has no GPE. All right? So this raises the question, what do we mean by lowest possible point? All right? So, in other words, to calculate gravitational potential energy, it's mass times the acceleration of gravity, which, by the way, I guess I might as well say this here. We're going to use positive 9.8 meters per second squared here. I'll explain why in a second. There's a couple ways you can think about it. But then times the height. All right? So how do you measure the height? Do you measure the height from the surface of the Earth, or from the ground that you're standing on, or from the center of the Earth, or what? And it turns out that it doesn't really matter, because usually what we're interested in more than the actual gravitational potential energy is the change in gravitational potential energy. And so as long as you're consistent with how you measure your height, it shouldn't really matter, all right? And there's a little note about this down here. So let's see. So the gravitational potential energy depends on the height and the mass, cool. And the GPE depends on your coordinate system. In other words, where you choose for your h equals 0 to be, all right? So my recommendation is this. Choose the lowest possible point in your problem to be a height of 0, all right? So in other words, suppose you've got, I don't know, maybe there's the ground and there's a table, all right? And then next to the ground there is a pit, okay? All right, and then there's, I don't know, whatever, a box of goldfish crackers, all right, sitting there. All right, so when you measure the height, my recommendation would be to find the lowest point in the problem, call that a height of 0, and then measure everything up from there. So maybe this is a height of, I don't know, maybe it's a 3-meter deep pit, and then maybe the table's another meter, and so that's a height of 4 meters, okay? And so that will keep things easier. Now, if you wanted to, there's no reason why you couldn't call the floor a height of 0, which would mean that the table would be a height of 1 and the bottom of the pit would be a height of -3 meters, right? Okay, so it doesn't really matter whether you use this blue number line or the red number line or whatever, but you just need to be consistent, okay? So, as I said, to calculate the gravitational potential energy, here's the equation, all right? So probably simple to do an example, all right? So let's go back to Carl and Dave, all right? So, Carl the cat has a mass of 3 kilograms. So Carl, he has a mass of 3 kilograms. Let's see, he's sitting on a balcony 4 meters high. So the height is going to be 4 meters. We will assume there that the ground is a height of 0. Okay, so that makes sense to call this height 4 meters. All right, and then let's find his gravitational potential energy. So GPE is mass times acceleration of gravity times height. So his mass is 3 kilograms. Acceleration of gravity is 9.8 meters per second squared. Notice I did use positive. All right, and then we're going to multiply it by the height of 4 meters. So here's the deal. Here's sort of why we can get away with making this acceleration of gravity positive. And we'll learn a better explanation of this once we get to work. But for now, if you want to think about it this way, if you wanted to make this acceleration of gravity negative, you could. But then you'd also make your height negative, because what you'd be doing is you'd be saying that your object has the potential to go down 4 meters, all right? And so the idea is those two blue negative signs there cancel, and as a result, we just don't worry about either of them when we do the calculations. All right, so multiply this all out, and you get 117.6, and the units we get are, well, let's see, we're going to get kilograms times meters per second squared times meters again gives me meters squared. That is just joules again, right? Okay. All right. So that's how you calculate gravitational potential energy. And then, same as we did before, let's mix some things up a little bit. What effect does changing the mass and the height have? Well, I'm not going to go through the calculations here, but you can see that the gravitational potential energy is directly proportional to the mass and directly proportional to the height. So any change in mass will equivalently affect the GPE. So double the mass, double the GPE. 10 times the mass, 10 times the GPE. And same for height. 5 times the height, oops, I just threw my duck. 5 times the height gives you 5 times the GPE. Okay? So here it says Carl is, shoot, we didn't even find Dave's kinetic energy, or potential energy. So let's see. So for Dave, he's got 2 times the mass. That means 2 times the GPE. So Dave's GPE is going to be this doubled. So what does that give you? I wasn't smart enough to figure this out ahead of time. 235.2. Okay, so there's the kinetic energy for Dave, right? He has double the mass. That gives you double the GPE. Okay. And then it says Carl gets jealous, so he climbs up twice as high. And that has the same effect, okay? So now his GPE would be 235.2 joules. Okay? All right, and then finally, if they are both on the ground, that means their height is going to be 0, and that means that their GPE would be 0. Okay? So, on my answer keys, I will always be assuming that the lowest point in the problem is a height of 0. Okay? All right, and I think this is the last thing here. We can work backwards, right? If I give you the GPE, find the mass, then we can find the height, right? All right, I know you can all do this algebra here, but be careful. There's a really common mistake I see people make. So check it out. If GPE is MAGH, then H is GPE over MAG. Grab your calculator and type this in. 300 joules divided by 6 times 9.8. All right, what I always see people do is they type into their calculator, they'll type 300 divided by 6 times 9.8, and that's not what we want. What your calculator will do is it'll do 300 divided by 6, which is 50, and then multiply that by 9.8, which gives you 490. That's not what we want. What we want is that, okay? So 300 divided by whatever 6 times 9.8 is. So let me grab a calculator. I didn't do this ahead of time. 300 divided by 6 times 9.8 is 58.8. And so you get 5.1 meters. Okay, so there we go. I think that is it. Oh, no, it is not. I lied. I apologize. This is for sure the last slide. Quick reminder. Notice that an object can have more than one type of energy at a given moment. Okay? And all of these, every time we talk about energy, we're talking about energy at one moment in time. Okay? For example, after I drop my duck, right? So right now my duck has gravitational potential energy, right? If I drop him as he's falling, when the duck is right, here, at that moment, he's still got GPE because he's above the ground, and he's moving, so he has kinetic energy, right? In fact, right now, the duck has both kinetic energy because he's moving and GPE because he's above the ground, all right? If you think about a flying airplane and all of the people in it, that has all the types of energy that we've talked about, right? Which brings me to the idea of total energy. Okay, the total energy is the sum of all the different types of energy that an object has at a given moment. Okay, so a flying airplane would have kinetic energy because it's moving, gravitational potential energy because it's way up in the sky, elastic potential energy because somebody on that airplane has a scrunchie in their hair, and the airplane has springs and stuff inside it, right? Obviously, there's electric potential energy with batteries and whatnot, and chemical potential energy from the gasoline. All right. Finally, most of the problems we deal with, we're going to be dealing with specifically what's called mechanical energy. Okay, so mechanical energy refers to I've never had a good definition of this, but it's widely understood to just represent the sum of the gravitational potential energy, the elastic potential energy, the kinetic energy, and what we'll deal with in a chapter or two, what's called rotational kinetic energy. All right, so that is that.